All right, fantastic. All right, thank you everybody for being here. This is our first talk, OTTER talk for the fall 2021 semester. So thank you all for being here. Joining us from the University of Manitoba is Meredith Sargent, and she's going to be talking to us on a beginner's view of NC realizations. Take it away.
Awesome, thanks Doug. Hi everybody. So first OTTER talk of a new semester, very exciting. I'm just doing a basic expository talk about non-commutative function theory, and in particular, non-commutative realizations. So we can start by saying what I mean by a beginner's view here. Why am I doing this? Well, first of all, because I am a beginner. I am just picking up a lot of my non-commutative world. So I'm doing this kind of from the view that it's good to have someone do basics, super computational examples, like taking everything out of the very formal, very abstract world where a lot of non-commutative stuff lives. If you start diving into non-commutative stuff, you'll notice that a lot of the papers on this are really abstract and done in full generality, which is great as like papers, but hard as like someone new to the material. So again, here's my caveat. I'm a beginner. Please forgive my inevitable mistakes and imprecisions here. I'm trying to give us an idea. So like I say, I'm going to demonstrate some trivial computations. I'm going to discuss obvious definitions, and we're going to talk about standard notation, all the stuff that when you go to talks about these things, everyone kind of assumes the audience knows, but that like maybe they didn't. So the other reason I'm giving this talk this way is that I want to demonstrate that OTTER talks can be expository. So I think a lot of people are uncomfortable talking because they're saying, oh, well, you know, I don't really know a lot yet. I'm still starting out my research. I don't have any papers. Well, that's not really the whole point. If you want to talk about your research at OTTER, like rad, do it. But if you want to just give a talk, you can do that too. I find that actually having to go through and write explanations and a talk about something is one of the best ways for me to actually learn it and absorb it into my head. I found writing this talk super helpful. So I have some ideas for other talks you could potentially give. Basically, if you're doing a reading course, grab something out of that. Tell us about it. I'd love to see this stuff. It's always nice to see a talk about something, even if you've seen it before. So some options here, I think interactor factorization and like Berling's theorem, that'd be kind of cool. You could talk about just an introduction broadly to the invariant subspace problem. It's kind of a classic. If you are into like composition operators, maybe boundary behavior, Julia Cara-Theodori, and like Danjou-Wolf points. So, and these are just ones that like I thought of really quick while I was writing this slide. If you have something you think is cool, you can totally talk about that. This doesn't have to just be your research. It can be a nice expository talk. And this is kind of a service to the community too. If you have something like this, then we have a set of notes and hopefully a video that we can send off to people and be like, oh, are you interested in operator theory? Here's a thing you can see, learn some basics. So yeah, you guys should give talks next semester. So since we're doing a very basic talk, we're going to start by setting up our world. We live in the world of square matrices. We want non-commutative objects because this is a non-commutative talk. And the first thing that we see when we're in college that doesn't commute is probably matrices. It's not necessarily true that AB and BA are always going to be the same thing. We do have to make sure they make sense. So we're going to restrict to square matrices. And we really don't want to be restricted to the size of our matrices either. We want to be able to use whatever size matrices our heart desires as long as they're square. So we are going to take this graded algebra of complex square matrices. I'm doing everything complex, and if you go into the literature, they usually do either real or complex, but sometimes you'll see things where they're working on like a generic field. But we live in this world, complex. So we're taking our complex matrices, each square matrix, n by n, and we say this is the graded algebra because at each level, things are pretty independent. 4 by 4 matrices kind of live in a different world than 5x5 matrices, kind of, but they're still square matrices and we want to be able to grab them. I have a quick notation note. I tried to be pretty good when I was writing this about using I for the identity matrix, but sometimes I have 1 there. That means it's the identity matrix unless I make a note that it isn't. Okay, so let's actually motivate what we're doing here. I just said we're looking at square matrices because we want things that don't commute. And why would we care about them not commuting? Well, we're going to try to plug them into functions. And in particular, let's start by looking at polynomials. We know how to plug matrices into polynomials. This is something that you may have made your linear algebra students do at some point. Like, okay, cool, here's a polynomial, plug your matrix in. Oh, we had to square it. That's very exciting. And oftentimes we show them this as a way to motivate doing like diagonalization. It's a lot easier if you have a diagonal matrix to do this matrix multiplication. But it's plausible that you would want to plug these in. But as soon as you have more than one variable, you suddenly really need to care about the order of your matrices. Remember, these don't commute. That's why we care about them in the first place. So we're going to talk specifically about non-commuting variables. So instead of just p of x here, I'm going to have variables that I could hypothetically plug matrices into, but I need to care what order they're coming in. In particular, a squared b is not the same thing as a times b times a is not the same thing as b times a squared, not in general. So now we just did polynomials. Let's actually make these NC polynomials. So first we're going to say, all right, let's take some variables. I need to have variables that I'll eventually plug things into. So I'll have x1 through xg be a tuple of g freely non-commuting variables. There's g of them because someone picked that a while ago, that we would use g for how many instead of n or d. So this is what we use.
I think it's Bill. You can blame him. That's as far as I know.
I was looking through a bunch of his papers and it does look like it's probably his fault. Like, it kind of makes sense because we're talking, like, you might want to talk about like n by n matrices, and later we'll talk about like d-dimensional things, but I still feel like it's weird. Whatever, this is the convention, there are g of them. And when I say freely non-commuting, what I mean is there are no relationships between them. If you have something that commutes, then you know that x1, x2 minus x2, x1, that should be 0. But we're not requiring that, and we're not putting other restrictions on these either. Now we need to get into words. If you actually go through some of the papers, I'll, when we put this up online, I'll have links to some of the references I used. If you go through some of the papers, they always title this section a few words about words, because they're being very funny. And that's what we're talking about here. This WG being the free monoid on the G symbols. Here's our formal definition. I like to think of these as indices in some very hand-wavy, air quotey sense. We're saying, okay, you take your tuple of variables, you raise it to the appropriate word. And what this does is it says, okay, how do I order my variables and what powers are they to? So here I have my x to the w1, that's x1 squared, x2, x3 cubed. And that corresponds with the word 1, 1, 2, 3, 3, 3, because I have 2 x1s, an x2, and then 3 x3s. And notice this is different than if I have x to the w2, x1, x2, x3, x1, x3 squared, where here this corresponds with the word 1, 2, 3, 1, 3, 3. A note, you can kind of see it up here. I talk about length of the word here is k. Both of these words are of length 6. This is kind of our version of degree, and again, air quotes, for these monomials. So sometimes I'll use the word, well, sometimes I'll say word interchangeably for both this w here and the x to the w, but really I'm talking about sort of the same thing. So, all right, we have defined our monomials. Now we need to talk about actual polynomials. So I'm going to say, all right, take C and join our non-commuting variables. We want non-commutative polynomials over C. Each element then can be written out as some coefficient times a monomial. And this series here, it's not really a proper series. We're actually saying polynomials here. Only finitely many of those coefficients are going to be non-zero. So here's an example I just wrote out really quick. We have 2 plus 3x1 x2 minus x2 squared x3 plus 5 x2 x3 x2 plus 7 x1 x3. So notice we're not actually combining these two terms, even though they have the same number of x2s and x3s, because it's non-commutative. These monomials are different and we can't combine them. Now, we also want to talk about rational expressions. Again, when you're teaching like calculus or whatever, you start out saying, oh, polynomials, aren't those wonderful? And then we build rational expressions from polynomials by saying, okay, well, in our one variable case or the commutative case, we're saying rational functions are of the form polynomial over polynomial. So an example here, I just took a polynomial and put it over another polynomial. Sweet. Here's another one, a polynomial over a polynomial. And in this case, I'm able to reduce out that x plus 1. This is important. Remember, this is one of the things we always have to have discussions about in calc classes. We need to think about our domain. So the domain means these aren't exactly the same function because they don't have the same domain, but they are equivalent expressions on domain, like on the intersection of their domains, they are the same. So in some sense, these are going to be the same, but like not exactly. Now, instead of doing polynomial over polynomial, since we now have matrices, we can't divide things and our order is going to matter. So instead, we're going to talk about our non-commutative rational expressions as anything you can write down using sums, inverses, and parentheses. These are formal objects. So this just means, can you write it down? Sweet, that's a rational expression. I have a bunch of examples here. Some of them are nicer looking than others. These last two in particular probably make you rather sad because you can't take the inverse of 0. And this thing is just 0 by another name inverting. That's no good. So these are what we call degenerate. So this means there's no matrices on which they can be evaluated. But again, we're talking about formal things here for our rational expressions. So it's just anything you can write down. How are we doing so far? Okay.
Question about the rational expressions. So there you have 1 minus x1, x1 inverse. So you're not simplifying, right? These are formal expressions.
Yeah, exactly. So this is what I mean when I say formal. I'm saying we don't simplify, we don't do anything like that yet. These are just exactly, can you write it? That's the expression. So yeah, as was pointed out, my 1 minus x1 inverse here, like I said, that's 0 by any other name, but we're not actually simplifying it. Okay, so again, let's do some more examples with these. Coming back to our one variable example, I said, okay, I can cancel out that x plus 1. I'm transforming it through algebraic manipulation. And then also these are equal on the shared domain. And in some sense, that means they're the same. I can transform them through algebra, and on the places where I'm allowed to plug things into both of them, they both give the same thing. So we can talk about something kind of similar in the non-commutative case. We're saying, okay, let's look at some rational expressions and maybe they'll be algebraically equivalent. So this first one that I've written down here, you can actually test this. Remember your how to invert matrices thing and actually do this inverse. It does come out the same. You change the order, you put the inverses on. That's worth writing down. This one I think is a little bit harder to see, and it's one of the examples that I've seen in a couple of different papers as a super obvious example where it's so easy to do the algebra. But I know that when I was first looking at this, I had a really hard time feeling in my heart what rules I was still allowed to use because things are non-commutative. So I'm actually going to go through the algebra. It isn't that hard. I just couldn't see it. So I'm going to go through and show us that just so we have an example floating around. Hopefully. All right, so here's our example. This is what we're trying to show, that y times 1 minus xy inverse is basically the same, or can be transformed through algebra into 1 minus yx inverse y. So first we're going to have a useful lemma here. If you have any word here, and again, here I'm using w and x to the w kind of interchangeably, but you can kind of split this thing out a little bit. Here's a hint for how to do it. You're going to add and subtract 1 on either side, and then factor your -1 here. And that'll allow you to get both of these expressions. And then just subtracting 1 from both of that lets you see that you can sort of pull that w through your 1 minus w inverse. And this is a helpful little fact. So now we're actually going to try to show our example, and we need to do a preliminary step. So our preliminary step here is just like this w up here. I want to pull my y in some sense through this inverse, but it's going to get stuck a little bit. So you can go through algebra here. I'll make these notes available, but basically what you're going to do is apply our handy dandy fact here to make this inverse look a little bit nicer. Then you can multiply your y through it, subtract some stuff over, and then factor as appropriate. Once you've done that, then you can say, oh, okay, well, I now know that I can like bring a y through this thing. So then I do basically the same thing here. You just get to exactly this point and get rid of the x's on either side. So yay, algebra. Like I said, it's not super complicated and intense algebra. I just, when I was first looking at it, was like, I have no idea how to do this. Fortunately, there's a way that I personally find much easier, and we'll get to that in a little bit. But first, we need to say, okay, well, we just said these things are the same in terms of algebraic transformations. But in our one variable case, we also talked about, okay, on the shared domain, I can plug things in. So that's what we're going to look at here too. We're going to say, okay, well, what's my domain? My world, broadly speaking, is matrices, right? Square matrices. So what I want to say is, all right, what's the domain of my rational expression and my domain of my other rational expression? What's the intersection of those? And in that intersection, do they evaluate to the same thing? If they do, the thing is called, these two rational expressions are called matrix equivalent. Sometimes you'll see it as M of C equivalent, because sometimes you also only talk about real valued matrices, but matrix equivalent. So then we want to talk about actual functions. Remember, these rational expressions are just, can you write it down? We're not bothering simplifying. We're not doing anything terrible. So instead, we're going to say, all right, I want rational functions, and I want to care about their intersections, their domains. So we'll say an NC rational function is going to be an equivalence class under this matrix evaluation equivalent relation. And we're also going to then exclude our degenerate cases like 0 inverse and 1 minus XX inverse inverse. Anything that has the empty set as its domain, that we don't care about, we're excluding it. Now, like I was saying earlier, there's another way of looking at these things being the same for certain rational expressions. We can talk about power series equivalence. And I personally really like this because power series make me feel safe. I understand how they work and I like them. So when I was first looking at our example from before, my first instinct was to say, that right there is a geometric series. So write it as a geometric series. Rearrange as appropriate. Hey, look, it's the other geometric series. Whee! This is great. However, you don't always have a power series expression for your rational expression. But when you do, things are wonderful. And that means we need to actually have some definitions. We're going to talk about formal power series and regularity. So here we're going to say C adjoin with double brackets, our variables, is the ring of non-commutative formal power series over C in G free variables. So here, when I say formal power series, I don't mean like, I'm not even thinking convergence thoughts. I'm just saying, is it a power series? Sweet. So write it out. It looks like this. I'm not going to think too much about convergence. Now, then I want to have a subset of that, or a subring technically. I want to have the one that is just the rationals. And if you want to think about why we might need to care about this, think back to Calc 2. E to the x has a power series, but it's certainly not a rational function. So we want to say, all right, let's focus on our rational functions. Those are nice. We know how to deal with them. We're only going to look at the smallest subring of our formal power series containing the polynomials and closed under inversion of things that you can invert. So a particular thing here, we can invert nice polynomials. So this is just doing exactly like our geometric series game, how one might go about inverting a polynomial. This is one of the benefits to looking at rational expressions, rational functions, is because dealing with their power series is comparatively easy. Now, when you took complex analysis, you talked about things being analytic or regular, and you talked about them being regular near a certain point. And we're talking about the same thing here. I'm saying, I want to talk about whether these things are regular at 0. And you can say, all right, well, regular at 0, polynomials are definitely fine, right? Polynomials are always fine. Then we'll say, all right, well, if I have two rational expressions that are regular, then I should be able to add them and to multiply them. That makes sense. That shouldn't ruin anything. And also, as long as a thing is like invertible, in this case, I'm saying R of 0 is invertible, then its inverse will also be regular at 0. You can think of this basically like analytic. You want to be able to take inverses of things and not have poles nearby. So similarly, if you've got an NC rational expression that's regular at 0, that is, we built it from polynomials and inverses of nice polynomials, that corresponds to some rational formal non-commutative power series. So your intuition is still okay here. Your power series goes with regular and regular goes with power series, and that's wonderful. So we also have that given two rational expressions regular at 0, if they determine the same power series, then they're matrix equivalent. They're equivalent with that matrix evaluation. So this is nice. It's another way to define our rational functions instead of just rational expressions. You can do your rational functions by saying, okay, well, I have to be able to plug in all the matrices in their shared domain and it has to work out to the same thing. That's our matrix equivalence. But if they're regular at 0, you can write down their power series. And if they have the same power series, then they're the same, which is nice.
One question. Is there a way to look at the power series coefficients and say if the power series is actually rational?
I don't know off the top of my head. My instinct says no, but I think this is unclear. Merrick, maybe you know.
I mean, yes, in some sense, but in the effective way, not really. It's the same sort of question with commutative power series. whether it's rational or not. But for the non-commutative ones, it's you don't have generating functions so much. I mean, this is the point, you get to realizations, and it's there's three different sort of equivalent ideas. I don't think it's very effective to look at the coefficients. You want to look. The answer is yes, but it's very difficult, and there's better ways to do it.
Right, because you're thinking about like, how would you build this power series? You're going to do it by doing basically repeated geometric series tricks, right? To be able to invert things. And so like technically you could hopefully stare at it long enough and be like, oh, this looks geometric series like, but like Merrick said, there's an easier way, and we'll get to it.
I guess maybe the thing you probably Meredith won't cover is the Hankel matrix. So you look at I guess this is the closest, you look at the coefficients, or you construct a Hankel matrix for the power series, and the series is rational if and only if the Hankel matrix is finite dimensional. So I think that would be the closest thing. And if you construct a Hankel matrix, you're really getting into this whole backward shift sort of thing, which exactly leads into recognizability and realizations, which Meredith will talk about. So the best way is the closest I'd say is the finite dimensional Hankel matrix. But once again, as soon as you do that, you've pretty much written down the other methods.
Yeah, so we'll be getting there when we talk about, like Merrick said, I'm going to do that when we talk about realizations later. The thing that's particularly nice is if you've got a rational power series, you'll be able to have this nice finite dimensionality. So get psyched, because we'll wrap up with that.
Oh, great. Thank you.
So I'm actually going to generalize further still. We're going to talk about matrix valued NC rational expressions. So when I say that, you're probably like, oh my gosh, no, we were just plugging matrices into these things. Is that not matrix valued? And I mean, yeah, sure, you get a matrix, but also no, because the size of the matrix you get out is going to be weird. And we want to be able to have our coefficients be matrices. When we wrote down our NC polynomials before, our coefficients were still scalars, so this looked very scalary. But I want to be able to have matrix coefficients here. This is definitely more matrixy than this. So when we say matrix valued NC rational expressions, I mean, I'm going to say, all right, my coefficients of my polynomials at least need to be matrices. And then we say, oh dear, if these are square matrices, the things I'm plugging in are square matrices from our world, then we have some distress because we then have to care about the size of our matrices. But the trick is that we're not going to do normal matrix multiplication between these coefficient matrices and our variables here. We're going to do tensors. One other note before I move on to our next slide is that scalars can be thought of as these 1-by-1 matrices. So all of the behavior that we've just been talking about with like regularity and all of this can be recovered from our matrix valued case. So, all right, let's start with an example here. This is the same example I just wrote down. We're talking here's a matrix times some variables plus another matrix times some variables. Really, we're not multiplying these matrix multiplication style, we're tensoring it in. So we would say, okay, take this x2, x1, x2, and stick it next to each of these entries in our matrix. Now, x2, x1, x2 is going to be some square matrix. So this is going to be a matrix of matrices when we're done. And you could think of that as also just a big matrix. Now, all right, I just did polynomials. Let's actually define that properly. I'm going to say the vector space of D1 by D2 matrix valued polynomials. That's basically these things. I want to have an element having a representation where it's P, W, X to the W, and my coefficients here are now matrices. Then I want to take those polynomials and use them to build matrix valued rational expressions. So I want to add and multiply and invert as appropriate, but I have to put in some restrictions because I only want to make sure I invert square matrices. So inverting this thing up here is going to be a bad time. And I need to make sure that when I'm adding things and multiplying, my dimensions work out. So I can build these things. They might be super weird looking, but I have to make sure my dimensions work out the right way. Again, note these are formal objects. I'm not simplifying, and things are allowed to be degenerate. Another important note here, in my first example, when I'm dealing with this nice, lovely polynomial where things are beautiful and easy, I was able to just pull my stuff into my matrix, and I could then add these matrices together. So I would say a matrix valued polynomial is the same as a polynomial, or sorry, is the same as a matrix of polynomials. This is not true necessarily for rational expressions. Matrices of rational expressions, where I have a matrix and I stick rational expressions in each one, those are not the same as matrix valued rational expressions. So that's a place where we need to be a little bit careful, but fortunately things will end up working out nicely when we restrict a little bit. Like before, we can talk about regularity. So similarly, regular at 0, if your polynomial is invertible at 0. Makes sense. Add things and multiply things. And then again, if you have something that's invertible at 0, then its inverse is going to be regular. Similarly, we can talk about matrix valued functions. We're going to think matrix equivalent, just like before, if they take the same value, which will be a matrix, on the shared domain. So you've got two expressions, you want to plug in matrices, and then you will hopefully get the same thing. So then our functions are going to be those equivalence classes. And again, we're going to say of the non-degenerate ones. I don't want to care about things that have no domain. So if you've got a regular matrix valued function, things start working out nicely for us. This kind of makes sense if you like squint a little bit, because in the same world here, regular should kind of go back and forth with power series in a very hand wavy sense. And you can kind of convince yourself, okay, if I've got a power series of matrices, I should be able to like kind of pull the sum into the matrix. This is of course formal, and I'm not thinking smart convergence thoughts, but you can sort of convince yourself. Similarly, any regular matrix valued rational function can be expressed by a matrix of regular scalar valued NC rational functions. So again, that goes back, same idea. You've got a power series of matrices or a matrix of power series. This is not precise, but I think it's a decent idea. Now, the most basic of our matrix valued expressions are what's called the linear pencil. And if you go to an NC talk, they will always start with this because it's, you know, our go-to object. So an analogy here, you're saying it's a line. I want to be able to have a line or a plane. It's not really linear in the sense that like your linear transformations from linear algebra class are linear, but it's a line. It's affine linear. So you do exactly the same thing. You say, all right, I want to have a constant term and then one term in each of my variables. My coefficients need to be matrices. I can talk about multiplying my pencil by other matrices. I have to choose them to be the appropriate size. When I do that, I say, all right, we'll do it in each variable. These variables x1 through xg can be moved around a little bit. We only want to have our matrices multiplying with matrices, and we're kind of distributing it over. Similarly, we're going to say, okay, well, here I started with this pencil and I found myself my lambdas. If you give me a tuple of matrices, I can then build a pencil. And for convention reasons that make some of our computations easier, we do the constant term minus our other terms. This just helps when you do some of the computations. So you can also then show that given your m here, you can find your pencil and it works out well with that multiplication. So our pencils, these are our nice go-to shape. It's sort of a line, but not exactly. And you can think about how one might go about evaluating these. This is somewhat easy to visualize. Now we need to talk about the actual content of this talk in my last like 10 minutes, realizations. So realizations, the whole thing about them that's nice is that you can take something that is nonlinear. I'm just doing a straight up polynomial, nonlinear thing, and write a matrix that contains all the information about this nonlinear thing, but that only has degree at most 1 inside the matrix. So here you can see there's my little matrix that I've built. I'm going to have to invert it. And then I have some vectors on the side so that it collapses down. So this is called a non-commutative system realization. These are things that are going to then have the form, just exactly what I've got written up here. A matrix times the inverse of a linear matrix, lambda is for linear, times another matrix. Now, there are different choices for matrix realizations of the same function. We talk about this a little bit more later, but it's just convenient to be able to linearize things. I think that is relatively convincing. Lines are good, lines are easy, linear. Now, a special case are what's called descriptor realizations. These are ones where you build the realization using a certain form. So in one of the references that I'm going to give you all, you have it defined as your realization here is a regular matrix valued rational expression of the form D plus C times something that's basically a pencil inverse B. So before I just said it's this C lambda inverse B part, that's what we'll mostly be looking at. I'm going to start neglecting our constant term here. So we have requirements about the size of things. The matrices that make up our pencil here are D by D matrices, as is our matrix J here. And then our C and our B, these have to be of appropriate size to multiply. And we allow for, in this case, D1 and D2 instead of just 1 by n and n by 1. As before, if we're doing this in general, we want to be tensoring in our matrices. So if we're evaluating at some tuple, we will tensor those in. We're not going to do proper matrix multiplication. We're going to stick them into our matrix. It's helpful then also to say, all right, this realization here, I have put a requirement on my matrix J, and the point of that requirement really is so that I can then make this monic. I can kind of divide my J through. And that's really nice because this thing you're inverting here right now, that now looks like a geometric series, right? So if you have 1 minus something inverse, you know how to write that out as a power series. And this should make you think, oh yeah, regularity, power series. Okay, I buy this. This seems like it makes sense. So here's an example. This is a realization that's built as a descriptor realization. I've just done the most simple, straightforward one I can think of. And you can use Schur complements to actually invert this matrix and get yourself a rational expression representing this rational function. So the realization is one way to look at a rational function and then since the rational function's an equivalence class, it may have lots and lots of representative expressions. A note here, this thing's regular at 0, right? You can imagine, all right, if I plug in 0 everywhere, nothing falls apart. I'm not trying to invert something I can't. So the key then is that regular rational functions have descriptor realizations. So you can build yourself a realization for a rational function this way. And this is kind of what Merrick was talking about earlier. If you want to know whether or not you've got a rational function, you want to say, okay, what's its realization look like? In order to actually show this, we need some machinery, and I'm going to kind of hand wave through some of this. What we're thinking here is kind of a backward shift. So if you look at my little blue text here, in the one variable case, we talk about backward shift as in lop off the constant term and scrooge all of the coefficients over. So that's exactly what you do here. And that's basically what we're doing with this version of our backward shift in big air quotes. I've got an example. Here's a polynomial that I've written out. I'm backward shifting by x1, x2. So this has no x1, x2s, so it goes away. No x1, x2s, no x1, x2s. This has an x1, x2. This one has an x1, x2, and then another x2. And this one doesn't have an x1, x2. So when I backward shift it, I only get the terms that have x1, x2 as a prefix. So, oops, too far. So then we're going to say, all right, the thing is recognizable, which if you, again, squint at the definition of recognizable, which says that you can write out your coefficients in this way, if you squint at that, you can say, okay, yeah, that does kind of look like a realization. It's slightly different, but it's the same idea. And we're saying that it has that if there exists a finite dimensional subspace that's closed under your backward shifts. So again, I'm not going to go through the proof carefully, but our idea then, in its soul, this proof is saying, okay, the backward shifts are linear transformations. And if I have a finite dimensional backward shift invariant subspace, then that linear transformation can be represented by a finite matrix. You do this in linear algebra all the time, right? You say, okay, here's a linear transformation, see what it does to the basis vectors, write a matrix that expresses that linear transformation in terms of those basis vectors. Like I said, I'll make these notes available because what I've really done is kind of translated the much more algebraic, much more abstract proof in one of the references into something that's, I think, a little bit easier to understand. So if you want to go through those, you can. Then we also have that our formal series, so a regular function, is recognizable if and only if it's rational. So you can have this descriptor realization if and only if you've got a rational function to start with. We'll be using basically that theorem that we just hand waved our proof through. We're saying, all right, we need a finite dimensional subspace. So if a formal series is rational, then we have an appropriate finite dimensional subspace. I'm only showing one direction of this equivalence. Well, in order to think about that, you say, okay, rational things, these are built by inverting polynomials and adding and multiplying. So we need to make sure that polynomials give us these rational subspaces. And then we need to make sure that if you add and multiply and take inverses, you still have nice finite dimensional things. Again, you can go through the formal proof if you want. I'll make the thing available. But polynomials, that's pretty straightforward. If you are, it's finite degree, so you can have finite dimensions in terms of how you can backward shift it. Similarly, addition and multiplication are relatively straightforward. Inverses require some work. If you look in the reference, they talk about this thing they call T star. There you're just basically saying, okay, do a geometric series trick. And that's basically what you'll do in order to show that inverses then allow you to do descriptor realizations as well. Now this is my second to last slide. I promise I'm almost done. One of the things we really care about with these are what's called minimal descriptor realizations. And I have our formal definitions, but what you should think is one-to-one and onto, right? I want to be able to get all of CD and I want my kernel to be just 0. So it's minimal if it's in some sense a bijection. Why is that good? Because minimal realizations give maximal domains. So remember how we had all of these different rational expressions? We had a ton of different rational expressions. They might all represent the same rational function, but have domain issues. You want to be able to say, all right, well, what's the biggest possible domain that works for this function? The realization is one way to have a function. So I can say, all right, well, if I have a minimal realization, which is the best realization I can get, then I should have the maximal domain. And in this example, you say, okay, well, here's a realization. This thing has maximal domain. You just need that matrix to be invertible. And there are actually a bunch of different rational expressions that go along with this equivalence class, but they do not have the maximal domain. So realizations, why are they good? They're good because they linearize things, and they're good because if you have a minimal realization, you can see the maximal domain. And like we were talking about before, this nice like finite dimensional subspace is part of how you see that you have a rational function. It's part of what characterizes it. So I'll go ahead and stop here, and we can go ahead and stop recording. And then if people have questions, maybe we can discuss.